Hey everyone, welcome to my demo lesson today on calculus. Today we'll be talking about derivatives. So can I get a show of hands? Who has heard of the derivative of a function before? If not, you might know what the derivative is under a different name. So the derivative of a function is its slope. Okay, this means our instantaneous rate of change of a function. So a lot of people describe this using different notations. So for example, if you have a function f of x, you can describe its derivative as f prime of x, or df of x over dx, df of x over dx, or dy over dx a little bit more simply, if our function is in terms of x and y, x's and y's. So let's look at what this looks like in a linear case. So let's say we have a function f of x equals x, right? So this is a very nice function, crosses our origin, and it's a linear function, meaning they're constant. Our rate of change is constant. Our slope is constant derivative. So if we think back to what the slope of a linear function is, we can describe it as our rise over our run between 2 points. So let's pick this point here, x1, its output being y1, right? So we have x1, y1. Let's pick another point here, x2, and of course its output, let's call it y2. So our point's going to be x2, y2. So we want to find our slope, meaning the amount that we rise in our function, divided by the amount that we run in our function. We have to find these two corresponding distances. So we use a formula, right? Our rise is our y2 minus y1 over our x2 minus x1. Where do we get these numbers from? So if we're seeing how much our function rises by, we have to take the difference between these two values here. This gives us our vertical distance between these 2 points, y2 minus y1. Similarly, for our run, we have to find the horizontal distance between our 2 points, which is x2 minus x1, right? x2 minus x1 gives us this distance here. Okay, this is a fundamental concept in algebra to help us find the slope of a function. Let's adapt this to a nonlinear case, which is what we study throughout calculus. So let's say we have a function here, f of x equals x squared. So this isn't as nice as a linear function, but it's still quite pleasant to work with. We have a parabola, right? Symmetry function. And let's just try to find its rise over its run, its slope, using a similar concept here that we learned in algebra. So let's take this point here, x, and let's say we run h units across to get to this point here, x plus h, right? So if we want to find our output, right, we just take f of x, right? So this gives us our point x, f of x. And our output here is going to be f of x plus h, right? So our point here is x plus h, f of x plus h. So let's find the rise over the run in these 2 points. How much does our function rise by? How much does our function run by? Okay. So we take our 2 points, and we have to find our m value. Our function rises by this distance, f of x plus h, minus f of x, and it runs by this distance here, which we described as h. So this is good because this gives us our rate of change for our function, but if we want to find our function's derivative, we have to find its instantaneous rate of change. Instantaneous meaning, if our function has a point here, we want to find, okay, exactly what is its tangent line? How much does this function change by at exactly 1 point? And so we do this by taking our 2 points, x and x plus h, and we're squeezing them closer and closer together so that they are essentially 1 point. And so we do this by taking our limit of our formula here, x plus h. We have to make our distance closer and closer to 0. So we have to take our limit, h goes to 0, of x plus h minus f of x over h. This is our derivative, because if we move our point down and down and down, so that it's right on top of the other one, this tells us exactly how much our function changes at that given point, x. Okay. So this here is our f prime of x. This here is our dy over dx. This is our formula to find the derivative of a function at a given point. So how do we apply this? Let's do this to find the derivative of our function x squared at any given point. So our f of x plus h, after we apply the square function, we get x plus h squared as our output, right? After we apply the square function onto x, we get x squared as the output. So let's just plug stuff in. So if we want to find our limit as h goes to 0 of f of x plus h, right, this is just x plus h squared. We're subtracting f of x, which is x squared, dividing this all by h. So this is a little unpleasant to work with. Let's expand stuff out a bit. So we have our limit as h goes to 0 of x squared plus 2 times hx plus h squared subtracted by x squared, right, which is moving this over. And we have to divide this all by h. So again, this is still a little unpleasant to work with because we're going to get an indeterminate form after we cancel out our x's. We have h plus h over h, which when we substitute in for 0, we get 0 plus 0 over 0 indeterminate. How do we combat this? We have to try to factor out our h to get h times, when we take this out, we just get 2x. When we take out 1h, we get h to the first power, which is plus h. We have h in our denominator still. Cancel things out, we get our limit as h goes to 0 of 2x plus h. This is a little nicer to work with. Let's plug in our h using direct substitution. We get 2x is a derivative of our function f of x equals x squared. So what does this mean? What does a derivative mean? So again, I explained this is the instantaneous rate of change of our function. So if we have our function 2x as our derivative, this is saying that, okay, if we have x squared, if we want to find how much our function changes at any given point, we can just plug that given point into our derivative formula. So let's say we're at 1 at our function, 1, 1. If we want to find how much our function changes at the point 1, we plug in 1 into 2x, we get 2 as our rate of change. If we want to find how much our function changes at the point 5, right, 5, 25, we have to plug 5 into our formula. 2 times 5 equal to 10. So our rate of change is 10 at the point 5, 25. So this is a derivative explained, and I hope that this lesson was useful. If there are any questions, please let me know.